Yes.
So last week we've been talking about the brushless DC motor. So we're going to page 12, I think. So go through really quickly about the brushless DC motor. The key thing we like to go for DC brushless motor because we can use electronic to replace the mechanical brush commutator. So that's why. So like this brushless DC motor, we can see that we mainly turn the motor inside out. So in this case, the winding can be in the stator, so that will be much easier for us to connect the wiring. So the wiring switching can be done by power electronics. So that's a key development why we can change the DC motor into the brushless DC motors. So basically, you can see that the topology will be like that. So in here, we're using a three-phase brushless DC motor. And of course, in the market, there will be many different phases, but three-phase will be one of the common one. So like in here, for three-phase, we use the inverter bridge to drive them. Each of the, with this, we call it half bridge. That means half of the bridge. Then each half bridge, we control one phase. So like in here, the motor, same as the other motor, we connect it in star or parallel. So in this example, we are showing the connection using the star connection. So the waveform, you can see that in here. So we try to inject the current to the winding. So the current injection can be fooled by the power electronics. So once we inject the winding current in here, the motor starts to rotate. You can see the back EMF. So when the motor rotates to the other part of the winding, we can also see the back EMF, but that will be in the other direction. So by using this switching pattern, we are able to control the motor in systematic manner, in three-phase manner. Each of the phase current will therefore contribute to the corresponding current, and also each time we have a two winding being conducted. So later on, we can see the switching pattern, how they look like. So if the back EMF is like that for each of the phase, the current is also like that. We can calculate the power level for which one, for any one of the phase. So you can see that when the motor being reversed, then the current and the back EMF also become reversed. So the power on this portion will also become positive anyway. So if you look at the three-phase pattern, so each time we have two winding are being conducted. So, and then you can see that each time with two winding, each winding will conduct and therefore produce torque. So that means actually we got two of the torque from each of the phase produced become the summation of the total amount of the torque. And the power level also become choice of each of the phase. So we also have two in here. For this kind of motor, if we use constant current to drive them, because current, as you know, that for DC motor is also proportional to torque. So we're going to, in the next chapter, we're going to show you how we're able to use the constant torque control as well. So basically, we can able to use constant current to drive the motor. So assume we are using a constant current, say I, to drive the motor, then so the power for each of the phase will be E times I, which is back EMF multiplied by current, because each time we got two phases being conducted each time, then we are able to have the total power become twice of the E times I. So I'm not quite sure you have done that. If you go through the string pattern, you can see that each time we have two winding being conducted, and then we try to turn on the transistor in some sequential manner, like in this pattern, we're able to systematically able to drive the motor in a symmetrical manner. So that's how we're going to try that. So later on, we got more diagram to show you how they look like, how we are able to drive the motor in systematic and one by one sequentially. We are able to, firstly, can make the motor to rotate, and also we are able to have more balanced torque and current among all three phases. But basically, this is the answer, how we can drive the motor. So if we're able to drive the motor in such a way to make them systematically and also all the current and the torque are systematically, we can able to analyze the motor in this kind of equivalent circuitry. So the equivalent circuitry we try to model them will be the same as the DC motor, what we have been using. But bear in mind that now every time we got two windings being conducted, so you can see that everything could be multiplied by 2 as compared to the conventional DC motor. So like in here, if the per phase resistance, we call the RPH, and the back EMF, we have the E. For the red phase, yellow phase, and blue phase, each of them will have their own back EMF. So basically, this back EMF are mainly produced by its permanent interact with the winding current. So at the moment, we just assume the inductive effect will be negligible, although there will be inductance for each of phase. At the moment, we're talking about in the steady state. We're not in the transient state. We can ignore the inductive effect. So for this modeling, we assume a voltage and also resistive from the winding and also the back EMF. So the modeling will be the same as what we did for the DC motors. And then we also have power source. So the power source could be a switching power source, but for every instant, every position, that means from that 60-degree column, so their voltage will be unchanged. But we were going to change them for each column of the operation. So like in this switching pattern, so for instance, as I mentioned, the current when turn on this winding goes through this winding, come back this winding, we turn in here. And then if we turn off this one, then we can also turn on the other winding. So anytime we make sure that we turn on 2 windings by appropriately turn the transistor. So that's why I can see that in this diagram. So we firstly turn on this one, next we have this winding and so on. We go into this sequential manner to operate them. So here we see that sensor will be important because we need to make sure the rotor rotates to a particular position, and then we can turn on the corresponding winding. So that means all this brushless DC motor, the sensor position will be important. They actually are synchronous motor because we try to synchronize. In a way, we can able to adjust the winding impressed voltage. So that's why when we say synchronous, that means the input frequency, we can able to have way to synchronize with the motor. If they're not synchronized, then the motor no way to work. If you done the lab, then you can see that if we connect with the feedback, so the feedback actually hold effect sensor to feedback the rotor position. So the rotor position will tell the controller where and which location the PM is, then can turn on the corresponding transistor. Without that pattern, then the driver no way you can understand the position. They not actually know which one to turn on. So that means by default, they will have their own really slow pattern to switch the transistor to wait until we're able to catch up with the sensor location. So that means I also label the transistor here, 135462. So that is the switching pattern. I can able to use it to give you a really quick reminder, a quick method how to understand which transistor to turn on and in this sequential manner. So you can see that this switching pattern is quite useful. We have been using this switching pattern for this brushless motor. We also use that for some square wave control of the induction motor too. I haven't teach you how to control the induction motor yet, but for switching pattern for some simple induction motor, we can also use this switching pattern to turn on. Then the motor will rotate in such a sequential manner. I'd like you to go home to check how we're able to use that switching pattern able to provide this switching operation column. So you should able to figure out, you need to spend some time to work out which one to turn on which. Then you should able to see that switching pattern will be related to this switching position. But of course, even though you don't understand it, you cannot work out, you can still work out the equivalent circuitry in the next few pages. But anyway, so this kind of the motor, we try to make it more look like a three-phase magnet. So each transistor will turn on for 120 degrees, and then the transistor current will flowing through a pole-pair transistor. For instance, if we turn on transistor 1, it goes in here, then this current need to return to certain path. So for instance, you return through the Y path, then you can able to turn on through the transistor, a pole-pair transistor in the other phases. And then you can also turn on through the transistor for the other pattern. So there's when we go to here, the transistor current can turn on in here, can turn on through this transistor pattern. So we sequentially to repeat the pattern until we can see complete all the 6 column of operation. So you can see that here, all the switching here more look like we try to replace the commutator. What we learned from the last few chapter for the brush and commutator, they're only single phase. But now then we are using 3 phases, so the switching pattern will be slightly more complicated, but the concept will be the same anyway. So here this diagram to show you which transistor being turned on. So you can see that how we using 1, 3, 5, 2, 4, 6 this switching pattern. Then you can say for this column which 2 transistors being turned on, and so on. Then from here you can therefore can work out how the current being flow in which winding and which transistor. So how I memorize it, I just memorize this 1, 3, 5, 2, 4, 6 pattern. So this pattern will be exactly the same as what we written down here. Okay. But anyway, so I will let you to spend your own time to work out the switching pattern. I don't think will be complicated. You just spend some time to work out to draw the current to see which one to flow through which transistors. So anyway, now then let's work out the mathematics, how to work out the equivalent circuitry. You see in the exam, if usually I will ask you some question like this, how to work out some calculation example, maybe some equivalent circuitry. And in here, I may usually ask you to work out how the switching position, like which transistor turn on and turn off. I may also ask you how the current being flow. Quite straightforward. If I ask you which transistor being turned on, when you turn on these 2 transistors, of course, you can see that the current will flowing through in this way, right? Will be like that. And then we can also start to, if we turn off this one, if you turn off this one, this transistor must be turned on, right? So that means, so you can therefore work out how the current, if the current flowing in this way, this current cannot be stopped instantly. The current can, therefore can flow through this diode to complete the loop. So there's a lot of the capability in here, how the switching pattern will look like. So you try to go home to work out how that pattern. But now then, let's spend more time to work out the equivalent circuitry. So we have the basic circuitry here. The voltage input are equal to the back EMF plus the voltage drop in the resistor. Because every time there will be 2 phases being turned on in series. So this motor we are using Y connection. So if Y connection, you can see that then the Y connection every time will have at least two windings are being connected. Of course, if some motor are connected in delta, you need to think carefully how many of them will be turned on, which one will be turned on. Okay, but Y will be easier for you to understand, to explain the operation. If Y, then there will be one will be turned on, the other two will be connected in series. So that's more complicated. So anyway, if you go for the Y connection, then in this case, in this R dash, actually we will have two resistors in connected in series. The back EMF as well will have the two back EMF connected in series. So bear in mind our switching pattern here will make sure that even though the connect in such a way, the current looping in here, these two are actually connect in superposition, connect in series. They're not canceling out. They're connected together. That's how we connect them. So that is to say, then we have E dash here will be equal to 2 back EMF. And every time you can see that the input voltage, VDC, have to pass through two transistors. So that you can see that in here every time must pass through two transistors. So we also need to accommodate for the two transistor loss. So as VOS mean on state, mean on state voltage for the transistor. So the on state transistor is depend on which one you use. Can be from 1 volt to 3 volt. So depend on which one you use. But for my example here, I just use 1 volt to simplify the calculation. So now then, the back EMF, of course, is the same equation, unchanged. The torque is the same equation, but this is only for per phase, each of phase. When we have this omega, when we have that torque constant, you produce its own back EMF. And similar for the torque, so each winding produce a torque. This torque will contribute to a particular winding. So because we have two winding there, so that means the total torque of the motor will contribute by the two winding in here. So that's why I can able to have two of each of the phase. That would be quite straightforward. We're able to get that. So again, the torque constant and the back EMF constant are the same. So this page will be really straightforward, exactly the same as what we did in the past. But everything we multiply by 2. But need to think about where the 2 come into. Sometimes we need to 2, sometimes we don't need to. But most of case, like the winding resistance, back EMF, even though the on-state voltage drop by the transistor, have to multiply by 2 anyway. So you can see that I also label them with the Y, R, and R bar, and B bar, B, and so there's a certain switching pattern to show you how the winding are being connected in this 160-degree manner. And then the other day, I also explained to you why the BMF will have a slope in such a way. Because whenever the PM are rotate to a certain phase, then the back EMF will be equal to constant because the K constant will be unchanged. But when we have this position move on to the next position, between them, then the magnetic flux, the north pole will change to south pole. So this change, we assume them will change the positive law to the south. So this assume them it will be very linearly. So that means the position in between we have no magnetic flux that becomes 0, but between them will be very linearly. But anyway, if we work out the corresponding power from here, because plus and minus will be cancelled out. So that means the power level from each of the region here will also have same power. The same power, this region becomes 0 power. So every time we have this power level plus another winding, we got another power from another winding. So that's how we work out the power. So now then the equivalent circuitry, you can see that when the input voltage after the voltage drop from the VDC become V dash, which will be after the on-state voltage for 2 transistors. And then this will pass through one of the phase, another phase. So that means in this case, we can able to have a 2 resistor and 2 back EMF being can cancel out. So the equivalent circuitry will be quite straightforward. It's the same as before, but more importantly, we like to understand more about the torque characteristic. For the back EMF, if you look at this diagram, you can see that the back EMF E dash is combination of the two back EMF for each winding. So this back EMF will be proportional to the speed. So this one actually will be proportional to the speed. So if you look at the torque speed characteristic, then we see that the speed will be increased in this way. Of course, the back EMF, this one, this back EMF will be also increased proportional to speed anyway. So you can see that that will be a linear rising linear curve. And then when we like to have constant torque, then the current will also become constant because torque proportional to current. So between them here, we got this is constant. The resistance will be constant fixed. So that actual voltage will therefore become the V dash voltage here will therefore equal to E dash plus I and then R dash. So that is the effective voltage we have here. So this also increase linearly upward. So now then, all the motor must have a limited voltage, like the voltage rating. So we cannot go over this voltage rating. So if we want to use variable voltage to control the motor, we can gradually increase the voltage until upon here, we cannot increase the voltage further. For instance, the motor is, say, whatever voltage, 48 volt, then we can increase the voltage from 0 to 48 volt to control the motor speed. But to an upper limit, we cannot control it anyway. So that's the maximum voltage we can able to limit. So after that, then we know that the voltage is limited. Anyone can tell me how much is under this curve. So, and then obviously we know that the torque we're going to drop similar to the field weakening we learned in the past. But in this brushless motor, the field is not going to drop because it's PM. We're still using PM motor. So could you tell me why the torque behaves as such? How much you understand this diagram? We know that in this point, you understand this curve, why the V are going up this way? Because proportional to speed. This is the speed. We assume constant torque, constant current in here. So up to this will be the constant torque region, like the first column we learned in the past. So if we compare to the induction motor, we have this curve, right? That's an induction motor. So that's a constant torque. That's a constant power. But we also call this the field weakening, right? So that's what we learned for the induction motor. We try to find a similarity between these two curves. But for the motor, we use at the base speed here, we want to further increase. So that's the omega C here is the base speed we try to operate up to. At that speed, then we have a limit because the voltage is being limited. We cannot control the voltage further. And then if we continue to increase the speed, what will happen? We cannot increase voltage. You can imagine if we have DC motor, PM, the thrust is unchanged. And then you try to continue to increase the motor speed, and then the voltage cannot be increased further. What happens? Which one can continue to increase with the speed?
First speed is going to increase, need the torque to decrease.
The torque will going to decrease. The question is how the torque is decreasing in such operation. You see, tell me why the E will continue to go up even though after the constant torque region. You can see that my line here, E dash continue to go up. Why is that? Can the back EMF continue to go up after base speed? Negative, what the big? Yes, because the back EMF is proportional to the speed and the K omega. K is unchanged. K is only controlled by the bracket thrust. The thrust is unchanged. So that means in here, if we increase the speed, the E must proportionally increase linearly, indefinitely. So even though beyond that speed, because the K is unchanged, omega is increasing, so the E dash here, the value also continue to increase. So what happens if the input voltage is unchanged? You cannot increase the input voltage from DC source. That's limited. The input voltage is unchanged. And the E voltage is going to increase anyway. What will happen? Which one cannot be increased? The voltage. We say the voltage we cannot increase further because limitation by the voltage rating from the motor or whatever. And then now we still want to increase the motor speed, want to overdrive the motor. Increase current. Current, yes. This is the voltage drop on the resistor, the winding resistor, IAR. So this is this one, right? R for the motor is unchanged, it's a fixed winding angle. And then you can see that the E voltage acting the voltage on the winding resistor is equal to input voltage. And the input voltage increase at this point, we can increase further. If further we increase it, then that means the voltage is limited. For instance, motor starts with 0 volt, the input voltage 40, we increase to 40 volt, that's it. We cannot increase further, we cannot anything more than input limit. So now then, this is the voltage drop. So that's to say this amount will be so that is to say I must be going to decrease. If I decrease, the torque will decrease. You can see that I will decrease in a very linear manner. You can see the curve on linear. So I will decrease linear with omega increasing. I decrease, the torque will therefore decrease in a very linear. And then you can see that when the torque go even further, the current is dropping. I haven't drawn the current waveform here. You can try it. The current will drop until a point that there's no more current. Current equal to 0. At this point, current equal to 0, right? Because the voltage minus the back EMF equal to the IA A, right? Now we have no current. So at this point, we don't have any current IA. The current for the motor becomes 0. The torque must equal to 0. So the torque should equal to 0 at that point. So we can draw a line between. You get that? So the curve will be not it's potential. This is proportional 1 over omega in this potential like curve. So this curve are proportional to 1 over omega. Right? But this curve are inversely proportional with the speed. So I also provide you with the equation. I like you to have a homework, try to divide this equation. So the concept is here, very straightforward, very simple to divide it. How you divide it, tell me what kind of the P0 this should be, what kind of omega log in terms of certain parameters. So that will be also part of the homework file. It's very straightforward too. I think in the internet probably you can find some answers somewhere. hopefully don't look at the written answer and then try to divide it yourself. After you divide, you fully understand the torque control and also so-called the constant power. This is constant power. Do you think that will be constant power? You think about that. This is constant torque. This region, what kind of thing will be constant? The I is jumping. The voltage is unchanged. So think about that. What kind of region we can call that? So you can compare these two operations. So for the constant and first kind of motor like the PM, this is also part of the PM motor. So when we beyond the base, then you see that the torque need to be decreased anyway. So we do have limitation. So this speed is only quite limited. So if you want to overdrive this motor, then we can overdrive it by a few times. But for induction motor, for other motor, we can actually overdrive them few times higher than the base speed. So this is typical curve for the induction motor. Even though the next chapter I'm going to learn will be switch reactance motor, then you should have these two standard column, constant torque and constant power, and then there's another region of even overdrive the motor further. But of course, this DC motor, because the first become fixed, you can't do anything, so the overdrive speed only limited by this equation. All right, any question after this point? So this text here mainly to tell you about what I discussed to you just now, the effective voltage. This effective voltage actually equal to our V dash, which is summation of E voltage plus the voltage drop on the resistor. So because we further on increase beyond the base, then this I must decrease in order to have a summation equal to input voltage V dash. So until a point here, I must be diminished to 0. So that means we don't have any torque. The torque will equal to 0. So we're able to plot this curve, become this equation. So I'd like you to divide T log and omega log in this equation. Yeah, let's try that. So let's look at another tutorial to see how we understand further about this DC motor operation. You see, brushless DC motor are very similar to DC motor. So everything are the same. Just the most different part will be only the switching pattern. So once you understand switching pattern, then that will be exactly the same. The equation is the same. All the torque equations are exactly the same anyway. So again, we got PM brushless DC motor and the torque constant is 0.12 and supplied by a DC source. And estimate the no low speed in RPM. And then when you connect to 48 volt DC voltage. And then the armature resistance 0.15 per phase. So now then that's per phase. So that means R dash equal to choice of this one, right? And the total voltage drop due to the transistor is 2 volt. 2 volt, that means each transistor will be 1 volt, totally 2 transistors, 2 volt. And then calculate the stored current and stored torque. So later I will tell you what's the meaning when it's stored then. That means what kind of torque it will be. Next, to calculate if the DC current is 8.2, when the motor is output 330 watt of mechanical power at 3400 RPM, the motor is now start connected, and then the total 2 volt drop again. Yeah. So the friction is 0.046, and then the supply voltage 48 volt, and calculate the efficiency of the complete dry system and the power component, loss component in the transistor and the winding and the friction and iron loss. And then we try to model the iron loss using a resistor. That's what commonly we try to use. So all these examples are very similar to this motor. Let's go through the answer quickly. Yeah. Firstly, combined torque constant 0.12. So that means we have V dash over K dash is our omega log here. So that means VDC 48 volt minus 2 volt voltage drop, and the Hawk constant become 383. So that is our omega log. So the low speed will be omega naught because in here we have without any IA current, armature current, so that will be our low speed. So that usually will be maximum speed we are able to achieve. So second part will be we try to calculate the at the standstill. So the resistance is 0.15, voltage drop per inverter is 1 volt. So again, 48 minus 1 divided by this one will be give us the current. So the current we multiply by a torque constant, that will give us 18.4. So that will be the standstill. Torque will be equal to this one. And then now the C part will be when the current is equal to 8.2 amp. And now the motor delivers 330 at 3400 RPM. So the friction will be 0.046. So that means the power input will be 48 times 8.2. 8.2. Then we can able to get the power. Output power, this one. So obviously the efficiency will be 83.8. So more complicated, slightly different will be here. We try to model all the motor by using core loss resistance. So let's see how we're going to do that. So the on-state losses in the transistor, we have two so that means one volt multiplied by current and two transistor, we have this one. Very straightforward calculation. And then the loss in the winding. So we use I square R losses. So each of the winding are connect to 2/3 of the time. I think you do know that 2/3 of the time. All the winding here, 2/3 of the time. So we multiply by 2/3. And then we have three phase. So the total losses, then we will be this one. And the frictional loss will be this one and multiplied by the speed. And then we got these losses. So that is to say the total losses will be all summed together will be this one. So we got all the losses. The remaining loss we haven't calculated will be the iron loss. So that means our P in, P out, the difference will be 64, and then subtract from this one should be our core losses. So core losses, how we're going to model them by a resistor. To do this one, then we can using, you see when the motor are connected in the Y manner. So this is the voltage here, and then divide by 2 will be this phase voltage. So that means look like V dash over 2. So that means, so for here we can assume again a T model here. So this is the T model. So RC here. So that means V squared over R, and of course there is also 2/3 of the time. We have 3 phases equal to 11. Then we can get the core loss equivalent to be 96 ohm. So that's the standard method how we calculate the core losses. So you can see that this example are very similar to the conventional DC motor. Everything becomes the same, but we need to adding many of the tools in here to make it become the brushless DC motor. Okay. Any question? This example are quite straightforward actually. So to conclude this chapter, then we say the key thing we learn here will be the motor are turning inside out of the conventional DC motor. So the key thing we have here. Once you turn inside out, then the motor winding in the past, we can now connect from the stator. But from the stator, we need to configure the mechanical switching. that mechanical switching are now being done by the power electronic. By that, for instance, for three-phase system, that will be done by the three-phase inverter to do that. And then we also could show you a switching pattern. So using my switching pattern, you are able to turn on, turn off all these transistors in a good manner, so that you're able, every time you turn on two winding. So the two winding, each one contribute their own contribution for the torque, and then the summation torque will be charged off the torque. So that's how we work out. So, but however, in here, we do need to have a voltage position. Without the voltage position, we cannot drive the motor. Just like in the lab, when you with and without the Hall effect sensor connection, the motor will behave quite differently. We cannot control the motor accurately. With the sensor, we are able to drive the motor in very high speed. Without the sensor, the motor don't know the position. It's just using a default method to drive them. So this kind of motor, you can see that the pattern here, we use 120 degree to drive them. That will be one of the standard pattern for three-phase motor. Even though for star connection and delta connection, we're also using similar 120 degree driving pattern to all the three phases. So this kind of motor, the key advantage will be firstly, usually with really high efficiency. The thing is, we don't have any commutator losses. So that means all the mechanical connection subsystem can become eliminated. The torque speed characteristics are really good. You can see that just now, we are able to control a very constant torque. Even though beyond the base speed, the torque will be decreasing linearly. So that means for control point of view, torque control will be much easier to control. For industrial motor, beyond the base speed will be curved in exponential decreasing, so the torque control are slightly more complicated. And the back EMF here, we decided to be more horizontal. So depend on the PM, how you design them. So the shape can be different. So because the motor we design here are using this manner. So the PM we locate occupied by 120, 120, and 60 here. So when this change over, the trapezoidal back EMF will change over from positive to negative. But of course, if you arrange the PM to another geometry, then the shape may not be trapezoidal. Then, so the motor are also supply a pure DC system. So the DC, after go through the inverter, we're able to control switching DC to the brushless DC motor, so that we play the conventional commutator. But anyway, so our free textbook, we don't have this brushless DC motor. If you want to go through them, that's another book. Will be a well-known brushless DC motor book. That's really famous book by Tim Miller from the University of Aberdeen in United Kingdom. But there will be a lot of material. You can go through them to understand more about the operation. All right, any question up to here? So let's go to the next section about the control method for brushless DC motor.